Hey everybody, welcome back. So a little bit of housekeeping. I adjusted the camera. I moved it closer to the whiteboard. Kind of feels like right in front of my face right now, but it's a wide aperture, so looks like it's capturing it okay. But I moved it closer. I adjusted the sharpness a bit, the brightness just a bit. So hopefully you notice a difference. Hopefully it's an improved difference. Let me know if you have suggestions on better ways to do this. I did not go to school for anything related to videography, so this type of stuff I am an idiot about. So if you have thoughts, even very basic thoughts, please tell me, and I will make use of them. Now I'm recording a bunch of these videos at a time. I'm going to release them later. So if you make a suggestion, it might be a handful of videos before I actually implement it. But still, please tell me, because eventually, for the latter half of this book, I also have 2 other books I want to make videos off of. I want to make it as good as possible for viewers, so please tell me if you have suggestions. I'm recording on a Logitech Brio, what's it called? Brio MX? I don't see it. I think it's called the Brio MX. It's 4K, I don't know. So if you have thoughts on any of that, let me know. Okay, so what do we got here? So we've been talking about mods. We proved some facts about modular arithmetic. We discussed last time in what circumstances can you maybe divide out the k, and we're going to be working closer to an actual proposition, laying that out. But before we get there, we have to prove a lemma. So do you remember what a lemma is? A lemma is a result in math where it helps you prove a theorem or a proposition. It's almost like it's saying, yo, lemma help you prove that theorem. So usually it's a smaller, oftentimes more technical result, but this is our first lemma in this course. So we're going to prove this thing. It's going to be about primes and division and stuff. GCDs are going to be involved. And then we're going to use that to prove this division fact about mods. Okay, so it's going to have 3 parts. So if you're taking notes, go ahead and leave, just a second and third part about this long, and then you can start the proof after that. But in order to save board space, we'll just do one part at a time. So here's the first part. Let A, B, and C be integers, and let P be a prime number. Remember from last time, a prime is a number that only has 2 positive divisors, 1 and P. Of course, it would have 2 other divisors. There's negative divisors, right? Our definition of divides over here does not prohibit negative numbers from dividing positive numbers and vice versa. So so prime would actually have 4 divisors, negative P, negative 1, 1, and P. But the way it's usually defined is there's 2 positive divisors, 1 and P. And then you're composite if you're not prime, meaning you have more positive divisors. Another equivalent way to say that is if n is composite if n equals s times t for some integers s and t strictly between 1 and n. Like 6 is composite because it's 2 times 3. 2 and 3 are both bigger than 1 and less than 6. Okay, so here's the first part. If P does not divide an integer a, then the GCD of P and A equals blank. What do you think is that blank? What should go right there? Take a moment to think about that. Pause the video if you want. Yeah, the answer, well, what should it be? Actually, I'm also going to save some space here for some scratch work. So I guess I'll just write scratch. So here's some scratch work. And this will help us actually answer, what is the answer, by the way? Well, if all we know is that these are integers, P's prime, A, and A has the fact, P does not, it has the property that P is not dividing A. So what are the divisors of P? Divisors of P. The divisors of P, we just said them. -1, 1, sorry, excuse me. Start with the least one. Negative p, negative 1, 1, and p. So the GCD asks for, among all common divisors between p and a, which one is the greatest? That's what it's asking for. So we know p's divisors, negative p, negative 1, 1, and p. So the greatest possible divisor is p. The greatest possible common divisor is p, right? Because that's the greatest thing that divides p. So if it also divides a, that's got to be the answer. Because there's nothing greater that could divide both of them, because there's nothing greater that even divides p. Okay. So is p going to be the answer? No, because p does not divide a. So the one condition that we're given in this problem is that p does not divide a, which means p is definitely not a common divisor of both of them. So p can't possibly be a common divisor because it doesn't divide a. So p is not going to be the answer. What about the next biggest possible answer? 1. Does 1 divide a? Yes, it does. Right. So that's the answer, 1. The GCD of p and a must be 1 because you just first look at p's list of divisors and you ask which one of these could possibly divide, what's the biggest one of these that's a common divisor, meaning also divides a. Answer has to be 1. All right, so proof. This is proving I. So this idea is basically what we're going to be using to prove this. So we're going to say assume a is an integer and p is prime. Saying this at the start, I think I've mentioned this before, rehashing your assumptions is not required, but it's a good practice for early provers like yourself. P is prime and p does not divide a. Note that, so now we're basically going to go through this logic. We're going to say, note that the largest two divisors of p are 1 and p. Note that the largest two divisors, so the top two divisors of p are 1 and p. And that's by the definition of being a prime. Definition 2.16. Oops, don't need to underline it. Okay. And now we have to say, so those are the biggest two possible answers to this problem. But p is not the answer, because we assume p does not divide a. Since p does not divide a, p is not a common divisor. Of a and p. Okay, so we've ruled out p as being a common divisor. And so, what's the next biggest possible answer? It's 1. And so, since 1 does divide a, and we've already denoted it divides p, that answer 1 must be the GCD of a and p. Okay, end of proof box. Okay, so that is the way you prove part I. Pretty straightforward. Once you have the idea to first look at p's divisors and then say which of these are common, and then go from there. Okay, think about that. If you have any questions, see if you can work them out on your own. Apologies, we can't do a back and forth here. Let me pause the video, erase this, put up part 2, and then we'll prove that. All right, so Part 2 begins like this. If A divides BC, and here's the question, am I able to write then A divides either one of them, let's say C. Put a question mark. Is that a true statement? If A divides BC, then A divides C. Pause the video, think about it. No, not necessarily. Do you have a counterexample? Yeah, so the examples will vary. Here's one. 4 divides 12. I'll write 12 as 2 times 6. So 4 divides the product of 2 and 6, but 4 does not divide 6 or 2. So, yeah, not true. Can you think of a condition that we could add to this statement? So we assume A divides BC, and we assume one more thing, and then we can conclude that A divides C. Can you think of something that would do that? So A divides BC, and something, and then we can say then A does divide C. Kind of squeezed it in there, but leaving plenty of room. So what is that thing, do you think? Well, actually, let me go back to this example that I just erased. So 4 divides, what was it, 2 times 6? So 4 divides 12. Now we've been talking about primes. If 4 divides 12, what does that say about the primes within 4 and the primes within 12? Yeah, it says that all of 4's primes are inside of 12. Right? 4 is 2 times 2. 12 is 2 times 2 times 3. So all of these are in there. That's what it means for 4 to divide 12. It means 12 has all of 4's primes and perhaps some other ones as well. All these things about divisions, this thing divides that, it all comes down to prime factorizations. At the heart of all this integer number theory is primes. Like that's all it is. So what would it be? So do you see what's going wrong here? So 4 does divide 12. 4 does have 12 does have both of these 2's in it. But the problem is 2 and 6 each only have one of their primes, right? 4 does not divide 2 because 2 only has one of 4's 2's in it. It doesn't have both of them. And 4 doesn't divide 6 for the same reason. 4 only has one of the primes. When you think about that, then it's easy to cook up examples. Like if on this side I want 3 times 5, so that's 15. On this side I just have to have 3 be in one of the primes. I could literally write 3, or I could do 3 times something else, like another prime, like 2. 3 times 2 is 6. And the second number just has to have a 5 in it. So it could literally just be 5. I could write 5 there. Or I could do 5 times 2, 5 times 3, times 5, 5 times 7. I guess in this case I'll just do 5. So you see so this is another example. 15, so this number does have all of 15's primes, but the 3 is in there and the 5 is in there. So 15 doesn't divide each one on their own because each one has some of the primes but not all of them from 15. So with that intuition, do you see what condition would have to go here? You could say something like that in words. You could say, and all of A's primes are inside of C. But that's not exactly what we want because that's basically just saying our conclusion. The condition is actually going to be a condition between A and B. So you could say, so one way to guarantee that A divides BC, if none of A's primes are inside of B, then they all have to be within C, right? If A actually is dividing B times C, and if B's not helping out at all, then C must be doing all the legwork. C must have all of A's primes within it. Make sense? So, in order for that to be true, you could literally write that. You could say, and for all primes P such that P divides B, or such that P divides A, P does not divide B. So you could say something like that, like for all the primes within A, none of them are within B. Another way to say that is no primes divide B. So P dividing A, we want P to, if for any P that divides A, we want P to not be dividing B. So we could say something like that. But there's actually another tool that we've already been developing that says the same thing in a more succinct way. It's the GCD. If no primes that divide A also divide B, what would that say about the GCD between A and B? It'd have to be 1. The only way the GCD is larger than 1 is if you have a prime that's dividing both of them. So if there's no primes that are dividing both of them, then the largest thing is 1, right? 1 definitely divides A and B. So the GCD is always at least 1, but in order for it to be larger than 1, you'd have to have a common prime, which we're sort of insisting that we don't. Does this make sense? Okay, so that is the start of it. Now, how are we going to prove this? Well, we need a tool. And our tool, we need a tool that somehow connects GCDs and integers. And can you think of a tool that does that? Bezout's identity. Bezout's identity. Do you remember Bezout's identity? That says that that we do indeed have that there's this connection between GCDs and integers. All right, well, for your viewing enjoyment, I removed 10 seconds of me erasing, and I suppose I replaced it with 10 seconds of me telling you that I removed 10 seconds of erasing. Nevertheless. Okay, so 2. How do we prove this? How do we prove that if A divides BC, let's assume that. Assume A divides BC, and GCD of A and B equals 1. And somehow we want to get down to the point that A divides C. So what does it mean for A to divide C? Let me just put this at the bottom just so we can have a target. Well, by the definition, if we sort of go one step in reverse, this would mean that C is equal to A times some integer t. So this is what we want to aim for. So how do we do it? Well, as I mentioned, we have a tool that connects integers to GCDs. That's Bezout's identity. So by Bezout's identity, we can, what does it say? It says for any positive integers A and B, and we actually are going to use the same letter, so it actually is still A and B. There exists K and L, which are not used yet, very good, such that the GCD of A and B equals this AK plus BL. So there exist integers K and L such that, what does it say? It says GCD of A and B equals AK plus BL. So the moment it's just kind of a tool. We don't immediately see the way that we're going to go from here to here. But it's a good thing to write down, right? I mean, you should, at the start, you assume, you look at your assumptions and you see, well, can I apply a definition? Yeah, maybe. This could maybe be applied a definition. But you also want to think about, have I proven anything else that seems useful? And we actually do have this Bezout's identity, which does seem like it might be useful. So, and it will be useful. Okay, now, we've assumed something about GCD of A and B. It's equal to 1. Okay. So this is the same thing as saying 1 equals AK plus BL. Maybe I write so. Okay. So that. Are we closer to our goal? C equaling A times T? Well, we have an equation. That's good. It's a start. We have an equal sign. We've induced an equal sign. We want a C on the left. Do you see a way to get a C on the left? Well, we can multiply both sides by C. We know that's allowed. So so therefore, these are all words you can throw in with interchangeably. For mathematicians, it's good that it's good that there are some synonyms for thus and so and therefore, so that way our work isn't so repetitive. Of course, it still gets repetitive, these words, but nevertheless. Okay, so we multiply both sides by C. I put the C in the middle for a reason you'll see soon. There and there. It's not so it spells out ac, although that's a happy accident. The advantage is, well, what do we want? We want C equals A times T. Well, we have an A here. If this term weren't here, we could just say, oh yeah, C times K, that's our T. We're good to go. But we don't have that. We have BCL over there. Now, if we could get an A over here, then we could pull out the A, and then it's A times stuff. That'll be the T. Do you see? So that's the way forward. As long as we can get an A to appear over here, then we can pull out the A, C equals A times whatever's left, and that's our conclusion. So how do we get an A to appear? Well, it's always a good strategy to remember, have I used all of my assumptions? Whatever mathematician did this probably didn't throw in extra assumptions that are unnecessary. We did use the GCD of A and B. We have not yet used the A divides BC. And actually, it's going to be quite useful, because saying that A divides BC, by the definition of divides, which is definition 2.8, that means that BC is equal to A times some integer. I chose M for some integer M. By the way, don't forget to say for some integer M. You can't just introduce a random variable without saying what it is. So these short statements are definitely necessary. And now we're good to go. Now this BC right there can be replaced by an AM. So before we had C equaling AC plus BC, and now the BC can be replaced by AM. And now we can pull out the A, CK plus ML. And there you go. That's the C times T that we were aiming for. Okay. So let's say that. That had to be an integer though, right? So why is it an integer? That goes back to fact 2.1 that we proved, or that we stated at the very beginning of this course, or at least of this chapter. Since C, K, M, and L are integers by fact 2.1, so is CK plus ML. And now we have C equals A times an integer. So this, and that implies A divides C by the definition of divides, which was 2.8. This completes the proof. Got it. Okay, there you go. Does it make sense? Now, it requires a little bit of insight. I mean, the fact that we just started with this instead of that and applied Bézoos to that, not exactly obvious, right? I mean, oftentimes proofs are not just, here's the way that it works, you know, just start with this, blah, 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 you get to the end. Oftentimes, the discovery process of a proof takes time, takes effort. But, you know, eventually you would hopefully try, you would see, you apply the definition of this, you'd have that written down in your scratch work. You would say, well, I do have a theorem about GCDs. Let me throw that in. And then you sort of see how can I combine these together. And then you discover that this is the best way to set up your proof. But usually the scratch work would probably start with both this and something about the GCD until you figure out the way to weave them together. Okay. Think about that on your own. See if it makes sense. And then I will erase and set up part 3 of the lemma. All right, so part 3 is on the board. In fact, the reason that not the only reason, but the main reason that we did parts 1 and 2 is actually to set up part 3. That's sort of the main number theoretic fact here. 2 is useful as well, and once in a blue moon, 1 might be useful. But part C is sort of the main event. And in fact, you're going to see what I just said in play, because the proof of part 3 is basically just applying parts 1 and 2 in the right way. So what does part 3 say? It says that if you have a prime dividing B times C, then in this case, you don't have to you don't have to add any other conditions about GCDs. No, P does divide B or it divides C. It has to divide one or the other. Or both. In math, when we use an or, that's in almost every case, it's an inclusive or. We allow the possibility that both hold. We don't mean this happens or this happens, but not both. We mean this happens or both. So both would be satisfying this as well. Okay, so if P divides B times C, a product of 2 integers, then it must divide one of them. And thinking about our primes earlier, this makes sense because, I mean, what does it mean for one thing? Remember, when A divides B and C, it means that all of A's primes, all the primes within A are within B and C when you put them together. But that same logic applies here, but since you have a prime here, there's only one prime inside of it, right? The only prime inside of P is P, right? So saying that all of P's primes are within B and C means that the prime P is within B and C. So which one is it in? If it's in this one, then P divides B. If it's in that one, P divides C. If it's in both, well, it divides both. And as I just said, that still counts. Okay, so that's the intuition for it. That intuition is important. I mean, whenever you have a statement like this about numbers and divisibility and primes, you should go back to prime factorizations and see if that level of understanding makes sense. You know, math is a combination of high-level understanding, little details you have to work out, ways to prove it using only the things that you've done thus far. It's a combination of many things, but you know, you shouldn't overlook the value of understanding this from a higher level. You know, do I understand prime factorizations? Does it even make sense why this would be true? Can I just sort of reason it out based off that? Okay, so let's assume that P divides B times C. And the way we're actually going to do this is in 2 cases. So consider 2 cases. Consider 2 cases. And the cases are P divides B or P does not divide B. Those are the only two options, right? Either P does or P doesn't divide B. So when you phrase it like this, that does cover all the possibilities. So case 1, if P divides B, can you finish off the proof? Yes, we're done. We're trying to show that P divides B or P divides C. If we assume it divides B, then we're literally assuming that we're already done. So if P divides B, then we are done. That is what we wanted to show. I'm only adding the second sentence to make it clear that there was nothing else that we wanted. We wanted to show that P divides B or C. We assumed it divides B, so we're done. So that was the easy case. What if P does not divide B? In this case, we want to show that it must divide C. So that's our goal. So if it divides B, we're done. If it doesn't, how can we prove that it divides C? Well, I mentioned that we have parts 1 and 2 that we've already proven. Part 1 says if P does not divide something, then the GCD between P and that thing is 1. Okay? If P does not divide B, then by part I, the GCD of P and B equals 1. And why is that helpful? Well, what does 2 say about things where the GCD is 1? 2 says that if the GCD between two things is 1, and you have something, why am I confused? Okay, so the P is the A here. Let me start writing. So P is taking the place of A. So P divides BC, we're assuming that. And the GCD between P and B is 1. Therefore, P must divide C, right? So for any integer, including primes, if you replace P with A, this is now, we have the two assumptions, we can now state the conclusion. Is 1. Thus, we know that P divides BC, and the GCD of P and B equals 1. Which by part 2, implies that P divides C. So again, we are done. This "we are done" is actually, it seems so casual, but it's actually not uncommonly used in like math research articles if you divide it by cases or something. I've seen that many times. Okay, so case 1, if P divides B, we're done right away. If P does not divide B, well, you can apply part 1, which in turn allows you to apply part 2, and boom, P divides C, and we're again done. So now just a concluding statement. Something like, in either case, or in either of the two possibilities, that's a longer word than I anticipated. We have verified the result. So that's the end of part 3. Okay. Oh, I used to do this. Part 3 is done, and therefore the entire proof is done. That's just a me thing. You won't see that in any other books. Okay, so hopefully that makes sense. That's a lemma. Lemmas are used to prove the next proposition or theorem. So stay tuned. In the next video, we're going to return to this AK equaling congruent to BK. Yes, that is next. Implying this, and to say what is the exact condition that allows you to cancel the K from both sides. We will state that proposition next time. Think in your mind. Think if you look at this. Think if you can figure out what that might be. And then come back and we'll do the proof as well. All right. I'll see you then.